Let's look at the simplest C++ program. Many people believe that the execution flow of a program starts with the main function because main is considered the core of the program and then ends with return 0, which is seen as the complete lifecycle of a program. But that's not actually the case. Main has never been the real starting point of a C++ program. Before main begins execution, the operating system, kernel, compiler, and C++ runtime library have already been silently performing a complete set of complex and rigorous low-level operations behind the scenes. The hello world printed on the screen is just a small visible tip of that entire iceberg. In today's video, we'll start from the very bottom and see step by step exactly how a C++ program actually starts. When you type /program in a Linux terminal and press enter, the shell actually makes a system call. That call is execve function, and it's the first critical node in program startup. The kernel clears out and reclaims all the memory space occupied by the current shell process, and then fills that memory with the code, data, and other content of the C++ program we want to run. It completely transforms the original shell process into our program process, completing a thorough identity replacement of the process. From this moment on, the system switches to executing our program's code. This is the first step where the operating system kernel takes over the program, and it's also a key point where the transition from user mode to kernel mode happens. After receiving this instruction, the OS's first step is to read the program file. You can try this yourself. Type file followed by your program name in the terminal, for example, file program. After running it, you'll see output indicating something like elf 64-bit executable. This tells us that executable programs on Linux are in a binary format called LF, which contains all the essential information needed to run the program. Specifically, the LL file stores key details such as the program entry address, code section, data section, dynamic linking information, symbol table, and more. The OS strictly follows the ELF structure specification and efficiently maps the core sections of the program into the process's virtual memory space using mmap, memory mapping. Note that mmap does not read the entire program into memory at once. Instead, it establishes a mapping relationship between the file and memory, loading only the parts of code or data that are actually used on demand. This greatly saves memory resources. After that, the system gradually sets up the memory layout for the code and data segments, fully loading the program's core content into memory. This is the complete low-level process of program loading. Once memory mapping is done, the OS proceeds to prepare the program's stack space. This stack isn't allocated arbitrarily. It gets populated in advance with 4 essential components: argument count, the argument values array, system environment variables, and the auxiliary vector. The auxiliary vector is a detail many people overlook. It acts as a messenger between the kernel and the program, passing low-level information such as page size and the base address of the dynamic linker. Ordinary developers don't need to handle it manually, but it's indispensable core data for runtime initialization. All 4 of these components are absolutely necessary. With these preparations complete, the OS performs a crucial step, jumping to the program's entry address, but this entry point is not our main function. In the ELF file, there is a dedicated field called entry point, which explicitly marks where the program's first instruction should execute. Viewing it is simple. Keep practicing hands-on. Type the command shown on the screen in your terminal, and in the output header information, you'll clearly see entry point address, followed by a hexadecimal memory address. This is the program's true entry point. This address usually points to a fixed symbol called start. In other words, the function where program execution truly begins is start, not the main we wrote. This is a low-level truth that the vast majority of C++ developers are unaware of. The start function isn't code we write ourselves. It's a startup routine provided jointly by mainstream compiler toolchains like GCC and Clang, together with the system runtime library glibc, and it's implemented entirely in assembly language. During compilation and linking, the compiler forcibly binds it with our code. Even if we write an empty main function, this start function still exists. Its sole job is to prepare the entire low-level environment for the C and C++ runtime, laying the foundational framework for the program to run. It acts as a transition bridge between the kernel and the user mode runtime and is the overall bridge of the startup process. Inside start, several tasks are typically performed. First, it retrieves argument count and argument values from the stack. Then it completes initialization of the stack and registers. Next, it calls the C runtime initialization code. And after all that, it invokes a critically important core function called libc_start_main. Libc_start_main is the core startup function inside the glibc runtime, essentially the master steward of the entire program startup process. It takes full responsibility for initializing the entire C++ runtime environment. All preparatory work is coordinated by this function, mainly divided into 3 major parts. The first task, initialize the standard library. Commonly used items like standard in, standard out, standard error, which correspond to C++ sc in, C out, C error, are all initialized at this stage. That's why we can directly use sys out inside main without any prior initialization. It's already ready before main even starts. The second task, initialize the threading system. Even for single-threaded programs, the threading environment is set up in advance, paving the way for any possible multi-threading later on. The third task, set up the program's exit mechanism, for example, registering at exit handlers to ensure proper cleanup when the program exits. For C++ programs, there's another critical job, running the constructors of global objects. This is another common misconception. Let's take an example. Suppose you define a global string variable initialized to hello. Many assume this message variable is initialized inside main, but in reality, it's already constructed before main executes. This is because C++ has a dedicated mechanism for constructing global objects. The compiler gathers all constructors that need to run in advance and places them into a special section called init array. When program startup reaches this point, libc start main automatically iterates through this initialization array, calling each constructor in turn, completing the early construction of all global objects. Now let's summarize the entire pre-main flow. First, start executes. Then it calls libc start main. Next, the constructors in the init array section are executed, completing construction of all global objects. Only after all these steps are done does it finally call main. In other words, main is really just the final step in the program startup process. Before entering main, the OS, loader, and runtime library have already collaborated on massive amounts of low-level work. Main simply handles the last mile, executing the business logic. And the misconceptions don't stop at startup. Program termination is also different from what many imagine. When main finishes and returns, the program doesn't end immediately. The return value of main is passed directly to the exit function, which then handles the remaining cleanup. The exit function performs 3 key tasks in sequence. First, it calls all functions previously registered with @exit. Second, it runs the destructors of all global objects, releasing memory occupied by them. Third, it flushes all I/O buffers, pushing out any residual output data to avoid loss. Only after completing all this cleanup does the program truly terminate and the process fully exit. Clearly, main is just a small part of the program's lifecycle. Understanding this gives you a true picture of how program execution really works, from the OS to the binary format to the C++ runtime. This is how computer systems actually operate.